Hello, YouTubers. Today we're going to be studying sort of like a generator, a turbine, and I was looking into helix turbine, and it's kind of neat. I mean, they're small. I mean, obviously, the amount of energy will depend on size. So I would like to do a trial in my own version of this vertical wind turbine, and see what happens. So I'm gonna start with a design on my Solidworks. It's gonna be a small design, basically because I'm planning to do flow simulation, and the larger the more time it takes. I have to do kind of the mesh too small to get accurate result. So I'd rather do a small, kind of a, well, I would say an experimental scale, and then go progressively increasing the size until I can get my hands on it. Understand better what it's doing in terms of torque and power generation and so forth. So let me start with SolidWorks so you get a good idea of where I'm going with this. So this is what we're gonna be designing in SolidWorks. It's a tiny turbine. I'm gonna do this very quickly so that we spend a lot of time doing the flow simulation, but that's the idea. As you can see, it's a sort of like a headache blade, but twisted, as you can see. And so the idea is to push air through the bottom and get the air at the top and see what will be the torque and so forth. So let's start with a new project in SolidWorks and let's see how this is done, and we move on then to do flow simulation. Hold for 1 second. I think I'm right there. So let me start doing this. Let me start by the, I don't know, front plane. It depends where the wind will come. Let's say that the wind comes from the bottom. It doesn't matter. I mean, you accommodate your profile accordingly. But let's say to make life easier, so I go through the top here, and we're gonna start here, and from there, let's say that I'm gonna make a circle. So let's say that circle is about an inch or so. Let's say an inch, and so let me get that right away. Let's say 24.4 millimeters, and let me do the following. Let's see. Let's say that I'm gonna add a few lines here and there. Let's see. So let me add a line here, another line here, a line here, and let's see. Let me get that on a vertical position, and let's say that I will say that this is gonna be, I don't know, 2 millimeters. Undo. There's something not right here. Let me fix it. Yeah. All right. And now to you two guys is, oops, it's already one here. Let me get this out. There we go. Now let's do, let me center this so that looks better. Perfect. And let's make this size and this size equal. And let's make the length of this guy 100, and let's see, Actually, let me undo here for a second. Let me fix that so that it looks much better. So let's say that I'm gonna keep a distance from here to here of about, I would say, 6 millimeter. That would be okay. And now I think everything looks good. Yep. Mm-hmm. Mm-mm-mm-mm. 47, 41. Did I said that? Did I set 47? It was not 100. There we go. There we go. Now we got the whole measurements. Good. Now, let's do this. Let's use, I don't know, let's see. How many of these sort of bent I would like to have on my turbine? Circular. Will that be, let's use the center and entities 2. So that would be this, that, that, and that one. So that would be 4. How about 5? That might look better. 5. Sounds great. So let's accept that. And now let's do the following. Let's start to trim this so it start to look like a one piece. Mm-hmm. Mm-hmm. Good. Mm-hmm. Perfect. I think that we got everything. Now we're gonna accept that. We said yes. And the next, let's do another line. Let's see, where should I do that line? Yeah, that one looks good. I would say that would be kind of a right. And that's, let's do a sketch there. And that sketch, I think I need a line. And let me get this in front. Perfect. And now let's do from here to, let's see. Now, how long I want that? It's about 100 on the band, and so I don't know. Let's make this 400, 4 times. Now, excellent. I think that we got everything that we need. Now we go features. How about we do a sweep? And now this is one of those weird sweep that I'm planning to do. Let's see. The sketch here will be, let's see if I pick this, it picked everything, great. Now here is gonna be how we're gonna sweep. You see how it looks like? Look like one of those pallet type of turbine that you use in boats. Yes, but here's the twist. Actually, it's gonna be twisted, and that's the funny part of this. I'm gonna do, let's see, option. Mm-mm-mm. Mm-mm-mm. Follow path, twist profile. Specify twist value. And here is the funny thing. Let's see how this start to look like as I increase the, the degrees of twisting. See, start to look more like one of those Savonius or whatever you call it, those type of turbine that are kind of sort of like an impeller from a compressor or something like that. And so let's keep doing it a little. I think that I need more. That's 30, 36, 40. Let's see, looking better. More. How about if I put the number that might looks better? 60. Yep, it looks perfect. How about 60? That's good enough for me. So we accept that, and I think that looks super. I have seen this before in some places, and there's two. I mean, there's two directions for the wind. Typically, I mean, this the way I thought on this turbine is that the wind coming down from the bottom or from the top, and will make this spin clockwise. If wind come from this side, it will try to spin as well clockwise. So it can go from here, the wind speed, or from the bottom or from the top, from the side. I mean, this will behave very interesting. Nice to see what's going to happen in flow simulation. I think that we got this build easy enough to get it 3D printed and do whatever we have to do. I'm gonna remove this real view, so because it start to bother my eyes. So now that will do. Looks like one of those spinner for the washer machine. Kind of cool. All right, good enough. Now let's go to top plane again, and let's do here. Let's get this into my front so that I can make a circle that cover everything, because flow simulation require that you do a circle. I mean, you cover your object that you're going to be studying. So with that, we go features, extrude, and now let's see how this looks like. We're going to extrude this. Let's see, from the bottom up and a little bit down here as well, so that we extrude the whole thing. Let's see how that will looks like. I'm gonna extrude a little bit higher here, pretty much the same direction. There we go. So your spinner is well covered within that solid. Now that solid need to be on check here on the merge result. You cannot have it merge, okay, right? Because obviously you will lose the spinner inside, and this object or this solid that cover the spinner is only used for flow simulation. All right, that will do. I think that we're done here. So we're gonna accept that, and now we should have two objects. One of them is called the sweep. Actually, let's change the name so that we're gonna rename that as the turbine, and we're gonna rename this guy as the rotating body, because that's what they call it, the rotating body. So we're gonna rename that guy as the rotating body. Now you don't see this, the turbine is here. Just make this here, change transparency, so that you can see it anytime and you know what you're talking about. All right, that looks super. I think that we got this pretty neat. Now what we're gonna do is now do the flow simulation again. Small enough, there's not gonna be a lot of torque here, but the idea to make a small the unit, I mean the spinner, is because it's gonna take a lot of time on the flow simulation to do large unit. my computer is not top of the line, so slow. Only have a, I think it's a 5E Intel microprocessor, so it's going to be slow. I don't want to do things that will take days to get some result out. So let's do this small scale and let's see what happens. If it work here, it should work as I increase the unit to a large, to to a kind of a commercial size. If that's what you're thinking to do. So the idea is go flow simulation here, and we go wizard, and oh, I haven't saved it. Sorry. Let's save this, and let's save this as actually. Let's see. I have many folders here. Let's go flow simulation and let's create a folder for it. As you can see, I have a lot of, I have analyzed a lot of impeller and things of that nature. Let's create a new folder, and that new folder is going to call about turbine, and we go deep into it, and we're going to call this actually is a helic, or sort of helic. Oops, helic turbine. Let's call this rep 1, and we save it. And now let's see, am I ready to go? Yes. Go wizard now. There we go. Let's call this project turbine, helix turbine, rev 1. Use current, default, nothing here. Next. It's gonna be SI, except few things here and there that I like to change because make life easier. And one of them is wind speed. Let's see where we are. Velocity. Instead of meter per second, I like to go miles. Where is it? Mile per hours. Make life easier. And that's how we typically measure wind speed. And low and motion, we want to change that as well to make life easier. Angular velocity, I don't use rad per second, I rather use rotation per minute. I think that's getting there. Anything else to change? Nope. Next, it's gonna be external, not big deal here. Now fluid flow and rotation, excellent. We're gonna be using the local region averaging. Well, that's what Solidworks said, particularly because you have a kind of a constant distance between the turbine and the outside of the turbine or the rotating body. Since everything is constant, this is the best way to do it. I'm only clicking here to show the other stuff. There's local region and global rotating. Gonna be using local region. Next, let's see, do we have anything next here? It's gonna be air. We got air, nothing here. Humidity, you might add that as well if you want to, not at the beginning. Adiabatic, well, I mean, I'm not doing any energy balance, so I don't care about these unless you are working, like, for example, in a heat exchanger or something. So, but not in this case. And next, here, couple things. Let's see. What's going to be the direction of the wind? The wind can come from the bottom. I mean, you put this on a sort of like in horizontal position. The wind will come, from either side, or the wind can come kind of a crosswind from right to left. That's up to you. In my case, I'm gonna go with the wind from the bottom up, meaning that I want this to spin on the y-axis. Y-axis. This guy is gonna spin on the y-axis. Actually, it's gonna spin whatever the wind comes from. It's gonna, well, I have to fix that out. I mean, I have to clearly set. It depends on the position of this with respect to your coordinate. In this case, let me do a 3D here, isometric, just to ensure that we understand what we're saying. Definitely, this is gonna spin on my y axis. So careful here. The wind, depending of which direction the wind comes. For example, the wind can come from the bottom. That will means on the from the bottom up, that means that the wind is positive. If I put a number here in miles per hour, let's say that the wind is, I don't know, 30 miles per hour. That's the strong wind. 30 miles per hour. Now, coordinate system, you see, is pointing to the x direction. So this guy will rotate sort of in the x direction. That would be weird because that means that there's something here, an axle crossing this, and this is spinning like this. And it's not. It's not spinning in the x-axis. It's spinning in the y-axis. So be careful with the global coordinate system. Let's say OK. Again, the wind speed is 30 miles per hour. If I check this, you see this arrow? That arrow is telling me that wind is coming from the bottom up. If I change direction, like for example, if I put a negative here, minus 30, you see how the arrow changed? Because now the wind is coming from the top to the bottom, which is not, you can analyze this anywhere you want, but make life easier to understand the numbers, particularly the torque. It's kind of confusing at the beginning, so leave it like that. Now, there's a question here that I personally leave this checked. So, because this wind is relative to rotating frame, and the more I read about it, yes, this will spin at whatever velocity, but outside from this rotating frame, that's the wind speed that I'm talking about. So I will leave that check. Maybe you want to uncheck it and find out what will that do to your analysis. But at this point, I will leave it check. Now, let's double check this. That is on the Y. Yes, that's perfect. So I don't think that we have to add anything else. Pressure and temperature, basically atmospheric pressure and temperature. No big deal there. Finish. We're done. We wait until the wizard complete the setup. There we go. Now, still doing some work there. Now let me get this. You see, I would say the computational domain is huge because I only really care about things close to the spinner in this case. So let me get this smaller so that the computational time or effort that the computer takes to do this is not big deal, because otherwise if I leave that box that big, it's gonna take forever on this computer. Maybe on a supercomputer that will be a few minutes, but in this one, guarantee it's gonna take for a while. Let's see how that looks like. Try to make equal in both directions. So right at the center. Oh, that look good. Perfect in all directions. So we are done with that, with the computational domain. Let's get this, hide that out. Now, fluid subdomain, we don't have nothing to do with that. Rotational region, we do. Insert rotating. Now, here we go. We have two bodies, and that's the nice thing about it. That it's not the turbine, it's the rotating body, actually, the one that we need. That's done. Now, what will be the RPM? This is a big question. It's not a problem of Solidworks, it's a problem of how you want to handle this, because you have to specify an RPM. Like for example, if I specify 0 RPM, it means that these blades are not moving at all. So there's gonna be, I will say, that's the maximum torque that this blade will have. Maximum torque meaning no horsepower. No, you are not doing any energy generation. You are just holding the blade not to spin. But that gives you a good, that's a good indication of the potential of this unit to generate energy, so you can extract energy. The spinner doesn't rotate. You need to do some effort to avoid that. It's like having a brake on the spinner, so it will not rotate. and that will give you sort of what would be the value of that. Now, watch again for the direction of rotation. Here, let's understand this. When the wind hit this from the bottom up, you remember that the wind coming from the bottom up on the y direction, it will hit the blade. The blade will start to spin clockwise. This wing will try to run clockwise. You see, that's like the proper direction is clockwise. Here is showing you an anti-clockwise direction. If I put like for example, a negative value here of minus 20 RPM, you see, and that's the direction that this blade will rotate, because that's because the way the blade were designed, it will rotate that way. I mean, clockwise. All right. So, for example, if I put a huge number here, 2000, let's say 2000 RPM, what will happen? Well, the question is, will the wind sustain the 2000 RPM clockwise? Probably not. And you will have a torque that will indicate that for you to spin this blade at 2000 RPM, you have to spend energy into it. You have to apply energy, otherwise it will not spin at 2000. See? Now, if I put like zero value, what zero will mean? Zero will mean that you are holding this spinner not to turn, and there's some value of torque that you need to apply. And that will give you the sign of that torque. What is the torque that is required? As you allow the blade to spin, now you're extracting energy, but the torque will get to a smaller value, and a smaller value. There is a value in torque when it's zero, actually, that there's no torque, that is required, and you will say that the spinner is what is called free spinning. Free spinning, you are not adding torque, you are not extracting torque, and the blade will get to whatever maximum RPM possible, and you can find that value by doing sort of like you can do an optimization, or you can do several runs at different RPM to find out where is that RPM in where you have zero torque. Maybe 500, maybe 600, maybe 1000, I don't know. That's part of what you have to do in SolidWorks to analyze the what would be the behavior of the spinner here. Now, let's start with the 0 RPM, because I like to find out what's the sign of the torque. All right. Now, as you can see, this big arrow here, if the is the direction for the torque being positive here, it's go up. If the torque is positive, it's just a matter of how it analyzed that the sign. And it's because, in essence, when something turns counterclockwise, your right hand rule says that the torque is positive on the up direction. All right. Now, so let's say 0 RPM, and let's accept that. What will be the goals that I need here? The goals, insert global goals. I think that we can insert global goals, or we can insert, actually we can insert, how about insert surface goal? And on surface goal, we're gonna pick the whole turbine for that analysis, and we're gonna look for torque. Let's open this kind of a, it's gonna be torque here. That's the torque that we want in the y direction. Anything else? Mm-mm-mm-mm. I will leave it like that. hmm Now let's add, that was a surface goal. Let's add a global goal. Again, torque in the y direction. hmm That's it, just to have two. global mesh. Now, I don't want to mess with this. Typically, it's a value of default of 3. I'm going to leave it like that. If you increase it up to 7, that's going to take forever. 3 is okay to start and see whether results start to make sense. If a tiny unit like this, you start to see like a 100 watt, 200 watt, you are totally wrong. That will no, that's not, cannot be truth. So that's something that you can check just to ensure what's the capacity of the wind. There's some formula for to let you know if a wind has 30 miles per hour, what would be the maximum energy that you can extract from that wind. Typically, it's about no more than 60% is the amount of energy you can extract at a wind at a six at whatever speed, But there's some nice formula done that the number is about 59% or so, close to 60. Well, that's basically it. Now, so I leave it on 3, no problem there. Anything else that I want to do here? Before doing anything else, let's check on the solver here. I like to put the solver to work. Instead of one satisfied, I like to have everything satisfied, all of them. That will ensure that the travel is also put into effect to ensure that the calculation as they are the best as they can get. Give it okay here. I think that we are done. Global mesh, let's run and let's see what happened. Run. It will calculate the mesh before and then it will do with the solve. That's at 0 RPM. It's like somebody's holding the turbine not to spin. And let's see where I have 2 windows here. It pops in a second window. Let me move it to my first window here so we can see it. And let's see what happened. Complete the mesh. So now it's doing the study. Let's see how fast it can be done. And remember, what we are doing here is holding the turbine. And let's see how much torque by holding the turbine it will show up. It seems like it's finished in some of the internal iterations, but now it will continue, you see, because it's looking for the trouble as well to get everything properly converged. But the number is not changing much. So now we know we have a negative number. The idea is to look for probably a positive number here when I change the RPMs. Again, this is holding the turbine. This is a tiny turbine, by the way. I mean, I'm not doing sort of any pilot or commercial scale. The solver finished. So let's take a look at what happened at some of this result here. And let's start by some flow trajectory. It's gonna be the turbine, and it's gonna be velocity, and let's increase to 60 maybe. Let's accept that. All right, let's see. I can see some of the line bend. I mean, getting obviously to this side as air hit the walls of the spinner. Now let's put this on play. Only on the center I can see some yellowish color, meaning somewhere here. There's not much reduction on the turbine, on the wind speed. All right, so let's stop this and let's change the rotating region. In this case, let's edit that. Instead of 0, let's start to put some values in the direction that this spinner will rotate, and that will be clockwise. So I have to put a negative in front, and let's say that this is gonna spin at -50. And since this is kind of a fast study, we will do few by, sort of like I'm punching the number myself. And with that, we're gonna go run again. Be careful here when you set that. Run, now put new calculation. Mesh is unchecked because I haven't changed it, so you can reuse that mesh before. So it's a new calculation. We set run, and it's preparing for this second run, and we'll see to see whether these numbers start to change from negative to a positive or to a more negative value as shown here. The value before was settling about 0.8 negative, and this is settling to 0.7 negative. And we can cut this short. I mean, we know that it doesn't change much as when you hit in the progress bar here about that it already converged with the 47 iteration. That's more than enough. So we can bail out from here just to do this fast. So we want to stop it, for example, and let's say yes, so that I can save the result, and we are convinced that this is good enough. Now, as you can see, I'm increasing the spinner RPM, and the value of the torque is getting smaller. But now you are extracting power because it's spinning. The problem is that if it doesn't spin, then you are not extracting power, because in this case, power is torque times RPM in radians per seconds. And that's the important thing about that. The spinner needs to spin in order for you to extract power. So what I can do is go back to rotating region and change that number again to a faster speed, let's say -200. At -200, you can run again and change to new calculation. And as you can see, what I'm doing is trying to locate by hand where the spinner will rotate at its maximum RPM, in where you are not adding energy or extracting energy. See, 0.07, and it's dropping to 0.06 to 0.05. So definitely, as you can see, I'm extracting energy at this point. The torque got reduced because of the action of the spinner doing what it does, which is spinning, but the RPM have increases. So it's a combination between lower torque, high RPM versus high torque, low RPM. I don't know. So this must be a sweet spot in where you got maximum energy extraction, which is another story. But again, this is done. So we are getting to a point in where we feel certainly that we can get, let's say, 500, and probably it's positive already at 500. So you cross over where the maximum spin you get, like the free spinning. So let's stop here. Let's say yes, and let's go back to rotating region, edit definition, and we're gonna put like I don't know, -1,000. Can it rotate to 1,000 RPM? I don't know. So if you happen to see a negative value again on the torque, it means that you still can go higher on the RPM. So run, probably not. It doesn't look like it's gonna be, because it's already 0.03 negative, so it definitely will cross over. And now you will see probably a positive torque, a high torque, meaning that you have to put power into it in order to run the spinner at that high RPM. And we don't want to do that, obviously. This is for extracting energy. So dropping, 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 0.06, 0.04, 0.04, 0.02, bingo, on the positive side. Definitely on the positive side, 0.1, 0.12, 0.13, and it's increasing. So you see, At 1,000 RPM, you have to put power into it. You have to add energy to the spinner so that the spinner can rotate at 1,000 RPM. And it's kind of a, I would say, relative to what it does at no RPM, it's a high torque. You have to apply high torque. I mean, compare, I mean, relative to that, to the low zero torque. Oh, sorry, zero RPM. The torque was 0.09, was small, and this is you have to apply twice to make to to be able to spin the turbine at 1,000 RPM. So definitely now you can see that it's between two values, either between 300 probably 200 and 1,000 right now. That will do. Somewhere between those two numbers is the what I call the free spinning, and that will settle very quickly to know. This is what it's done. So in other words, SolidWorks in essence will not tell you what are the RPM. You have to kind of calculate yourself or understand how all this is related. So in order to do that, there's two ways you can do these kind of scenarios. Like for example, you can go here at the, let's say that, let's see, we can run a new parametric study, which is definitely one thing to do. And if you run a new parametric study, like for example, bingo, it will pop a window. And now, what type of parametric study you want to run? Like for example, a what if a scenario and the goal optimization. The what if a scenario, it will run as you know, like I was doing by hand, changing the RPM and then allowing SolidWorks to work on that, or doing a goal optimization. In a goal optimization, you establish what is the torque that you want. What type of torque? Zero torque. A particular value of what you really want. For example, you can extract energy. If you are extracting energy, you put a negative value of a given torque value, and eventually the system will find at what RPM the spinner will do so. Let's try a goal optimization here. If I'm trying a goal optimization, the first thing is what is the parameter that I'm going to be changing, and that's going to be this one, the rotating region. Let's open this a little bit more because I cannot pick it. Angular velocity, we're going to pick that one. What is the range that I think that will do the trick? Well, it looks like the range here, it pops 1 to the minus 1,000. Obviously, that's not going to be the case. Although I can try at that. Let's try that. Minus 1,000. And the other one will be 0. So, because I know between those two values, that would be the range to do this. Let's say I accept this. And now, let's say that the criteria will be, on this case, at goal from here. We can add one of them. They're pretty much close to each other. Let's add the surface goal. And now we want the target, we want 0, but then careful here. What will be sort of the range that you feel comfortable that you are very close to 0? I will say 0.02, or let's say 0.3. I want a 0, target of 0 could be negative up to 0.3 negative or positive 0.3. So that's good enough for me. Now, output parameters, we're going to use all of them. We accept. And a scenario. So the scenario, it will start to punch number automatically to a maximum 128 iterations. That's way too much. Let's say no more than 10. Otherwise, something is kind of weird. I would say 10 is good enough for me. And let's see, goals. That's okay. Scenarios. We are perfect. And what we're going to do is run. So the first is gonna punch here. It's gonna try the angular velocity of 0. And then it will punch the other one. 0, we know what it is. It's gonna repeat itself of what it did before. As you can see, these two numbers are pretty much close. Surface goal or global goal, they're close to each other. So, and let's see how well this system behave. Remember, we are doing this now totally automated because basically we know that at 0 we got maximum torque, which is a negative value. Then as we allow the spinner or the turbine to rotate at maximum speed, then we have to apply torque, and that's a positive value. So between the positive and the negative, we know that there's a sweet spot in where the turbine will sort of free rotate at a given RPM in where you are not adding energy or extracting energy. This is a small turbine. Again, I mean, these numbers are very small. Uh, if you multiply, obviously this one would be zero energy extraction because torque is pretty much a small number, but then the RPM is 0. So as shown here, if it's not rotating, you cannot extract energy at all. But it's just a way to let you know about this thing that the turbine will free spin at a given RPM, provided that you are not adding energy, like adding a motor or something to spin the turbine. That's not the case, or extracting energy. You start to extract energy, then the turbine will slow down, and that's the point. Pretty much done. Good. That was the first point. Design point number 1. It will populate all this information for us. There we go. Now it's doing the second point, which is the 1000, and you can see the torque. The target value was 0, but we don't got the 0, so now it's moving to do another one. The other point in the range is minus 1000 RPM, and so that crossover to the positive side. So it's sort of like have you used any method to do zero of a function, like Newton-Raphson, a second method or something like that, like our bisection method? It's pretty much, that's what it's doing. That's what I like to give, a range into this where I know for sure that the system will not fail. If I provide 2 points here, say on the negative side, there's no chances. I mean, maybe it will do it, but it's more risky because I know that it probably will fail. Numerical method like to have a sort of like they call it the sandwich method, in where you have one side, another side, on the negative side, on the positive side, so you know that the 0 lies within the two brackets, right? Sometimes they call it a bracket method as well. Sandwich method, the bracket method, pretty much the same thing. So now pretty much it's doing some calculation, but the torque, now this positive torque, it means that you are applying torque to the system. Now you are adding energy to the system so that the system can turn or rotate at 1000 RPM. And obviously that's not what we want. We want to extract energy from air, from the wind speed, which is 30 miles an hour. Let's see how this looks like. Hopefully, I don't know, maybe 500. I don't know what number will punch here on the design point number 3. That will depend on the type of method that this system is using. Bisection will be like 500, negative 500. But I don't know. Newton-Raphson might be something else. There we go. It's not bisection because it dropped to 315. So we'll see. Almost, yeah, this will do. This definitely will do. You see 0? Perfect, right on the money. Cannot get better than this. So that's actually the true spinning of this turbine is at 315 RPM. You are not extracting energy, you are not adding energy. If you want to extract energy, then the RPM will drop. This is done. Basically, we are done. Only with recalculation, this system got the right RPM for zero torque, meaning free spinning. Almost done. You can improve this calculation. I did this with a mesh of 3. Maybe this needs to be repeated with a mesh of 4, maybe a mesh of 5. But that will take for a while, and that's the part that I don't want to do that at this point. See, flow simulation 2022 solution converge. Okay, that's perfect. Now let's go back. Let's save this, and where we are, turbine, parametric study, rep 1. And we save all that data. And now let's take a look to some of these at free spinning. That's the third result, this one here. So meaning if I go here to gold plot, just to take a look at it, and we take a look here, and we show it should be about 0, the value, or the average value around 0 torque. Perfect. That's where you get uh, the 315 RPM, which is, I call it free spinning. I can leave it there, no problem. So let's take a look to some of the plot. Like for example, let's take a look to cut plot and see how that will looks like. And let's pick top plane. Let's see where is that. Right at the bottom. I want to pick right in the center. So we take a look at that. And contour, vector, 10, about, I don't know, maybe 50. And let's take a look at that. Pressure, no. 1. Velocity. Okay, anything else here? Look good. Let's apply that and let's see. Too much red here, meaning that I'm at the maximum velocity and it's a waste of energy, at least at that position. I don't think it will change much at the top. So meaning that this turbine is wasting a lot of energy. So I need to perhaps twist it more. We'll see. Now, the minimum seems like it's around, I don't see any green here. So I can definitely improve this. And let's see, did it open? There we go. Now, let's see. That's 20, good. How about this one? 30, perfect. So now let's see how that looks like now. Oh, much better. You can see the different color here around the 30, a little bit less and less. But here inside, let's get some of this stuff out. Let's see. Let's hide this, and also let's hide that, so we see precisely what's going on. See, this is the energy that I'm talking about that is not doing much. So maybe if I bend a little bit more or twist a little bit more the impeller for this turbine, it will work better. I can extract more energy out of it. Well, I mean, this is work in progress. I wasn't expecting much on this kind of quick design Helic turbine, and easy to do a 3D printing on it and just do some testing and see what happens. But again, this is just the idea of how that looks like. And again, the 315 is the RPM in where you are not adding energy or extracting energy. If you want to extract energy, the RPM will drop to obviously the minimum, which is 0, and this is the maximum torque that you can get. Is around negative. Well, don't worry about the negative. It's just the way that the the torque is analyzed here on this SolidWorks, but it's about 0.08 Newton meter, and obviously that's maximum torque, meaning no energy extraction at all. You have to have something, like a given RPM to get that. So you need to do another plot in where you plot, for example, watts versus RPM to get that where the maximum will happen. Well, more than enough. Again, I appreciate you for watching this video. Have a great day. Bye.